Hello. Today we are going to start off with electrostatics, as we've done, as I promised you yesterday. And from today, this will be our main focus to finish off electrostatics from basics to advanced. Okay. So let us start. So electrostatics. So electrostatics mostly concerns with the charges at rest. We are going to discuss charges at rest. Okay, so we are going to discuss the charges at rest, and mostly we are going to focus our attention towards a few of the very important topics like electric field, potential, uh, Gauss law, and similar such topics. Okay, so mostly our discussion will remain there. Okay, we'll go very thematic, and what I will assume that your prerequisites are done, and your prerequisites, I believe, would be at least, if not more, you should be at least acquainted with standard 12th NCRT level of knowledge. Okay, so if that is done, I think you will be able to figure out everything that I'm saying. Although this is my promise that I'll keep my lectures very simple. I'll keep them very basic, so you don't need to panic. But still, if standard 12th NCRT level knowledge, or you have some know-how about all those things, you have some know-how about how to handle vectors, I think things will be easy for us. A little bit of uh, prerequisites of vector calculus, and that for that you can just refer Griffith. So you can just refer Griffith. Dirac delta function, I've already done a few lectures over it. So Dirac delta function, I've already done a few lectures. I will still recap you everything. Like I'll recap you vector calculus, I'll recap your Dirac delta function, I'll recap you even prerequisites. So that is absolutely fine. But still, if you just do away with these prerequisites on your own, then things would be easier on my end. Okay. So I will start from basics only. So this is my title of the lecture, or probably the series that I've initiated. This will be electrostatics, electrostatics from basics to advanced, from basics to advanced. Okay, so this is our topic that we have started from today. Now, you must be aware of something. You must be aware of something called as force. Okay. Now, instead of force, you know from your standard 12th also. So this is what I have done. I'll recap you that we are starting electrostatics from today, and mostly we'll discuss charges at rest. So electrostatic itself is study of charges at rest. You don't involve some dynamism here. The prerequisites that I would want from you is at least standard 12th NCRT. If you're done with it, it will be good for me. Vector calculus, just a few pages, starting few pages, like around 10 to 12 pages, you can find vector calculus. Griffith has mostly done more of physics kind of thing. So at least for a motivation purpose, it will be good for you that you just go through the first 10, 12 pages of Griffith. Grad delta function I've already covered. Although I'm making a promise that all these topics I'm going to redo as I do electrostatics. And this is an important topic for any of these competitive examinations that you are fighting for, because like this is a very basic topic. Okay, and mostly students, I have found in my teaching experience, I have found that mostly students struggle a lot in this particular topic. At least entire EMT, mostly I found people struggling. So, so what my target is, somehow I'll make things conceivable for you, but it would take time. Let us see how things will go on. Uh, the books that you can refer probably is probably H.C. Verma from Standard 12th. I don't know. I've not read this book I've not read this book. So, but I found that many people recommend this book, so I'll recommend it to you. And another book that I would find is I find good as Griffith. Okay, and some selected reading of Jackson. So Jackson, I'll tell you what selected portions you need to read. Selected portions of selected readings in from Jackson. Okay, so this is something that if you want to self study. Okay, although whatever I'll teach will be more than sufficient, but still, if you really need, ki nahi, I want to know things from where things are being taught. So mostly I'll follow at least these two books. Instead of HC Roma, I studied in my standard room from Wrestling Holiday. So I keep that book along, but many people find this very comfortable. So you can go with this book also. I have no issues. Overall, these will be the books from where we are going to study things up. Okay. So electrostatics, as you are aware that initially your life started with force. Okay. Your life started with force. So you can say that if I have to find interaction between two charges, if I have to find interaction between two charges, then I had something called as force. So I can find what force is being exerted by one charge on another, and I can describe something called as something. I can describe what sort of interaction is between two charges. Now, what happened is, if I want a definition, of effect of, instead of this interaction between two charges, if I want to find an effect of one charge, or probably a charge distribution, or probably a charge distribution, sorry, charge distribution at a point in a space, at a point in a space, then I would need something called as speed. So instead of force, now you have speed. Okay. So instead of force, the force usually had something to do with interaction between two things, or probably interaction between two or more things even, but it would involve that, let's say there are two charges. What is the force between the two will govern the interaction between the two charges. But instead, if I want to know, okay, let us say that this is my, let's say, charge q, and as soon as it is placed, it is going to propagate some kind of field in the space, and because there's a field, so there would be some value at some distance x comma y comma z. Now instead, if I want to find effect of this particular charge, or probably if I don't take a charge, if I take a charge distribution at a point in the space, then this particular quantity is being defined, is called as field, not force, but called as field. Okay, so this is a vector description of this is a vector description of uh, a sort of vector description. That is, if I want to find a interaction between two charges, I can find it using force, that is a Coulombic force here in particular. And instead, if I want to just find effect of one charge or a charge distribution at a point in a space, then I'm required to find what is called as field. I'll come to this field also, but later. Just recapitulating or revising what you've already done. Now, another way of quantifying your what you can say interaction between the two charges, you can have something called a scalar description. Now, what does scalar description mean? Now, instead of having force, you have something called as potential energy there. You have something called as potential energy. So what does potential energy describe? Again, potential energy describes a scalar way of saying what is interaction between the two charges. So it is a sort of interaction energy. So interaction between the two charges, scalar wise, would be governed by something called as your potential energy. And a scalar description and a field sort of analog here would be potential. Now, instead, if you want to find what is the effect of one charge or a charge distribution at a point in the space, then this potential energy will be replaced by something called as potential. So what does potential represent? Potential would represent effect of one charge, or probably a charge distribution, whatsoever this is the case, charge distribution at a point in a space. Okay, so what I would recommend you on personal scale, because what's happening is I'll keep on doing difficult or rigorous problems. So what you do, as and when I go on, like say for example, today we are doing field, probably tomorrow we'll be doing potential. You just go through some solved examples of HCM and at least solved ones for Griffith. At least solved ones, you finish them up, not unsolved ones, because probably in your busy schedule you'll not be able to finish everything up. So you just do Griffith or just do HCM solved ones. Jackson, you just don't attempt. I'll take care of this particular book. So therefore, I've written selected readings from Jackson that I'll take care. Just do what you can do is you can just go on doing at least the like solved examples for both of these. So if you do these things, I think you will be able to clear the exam, and otherwise you will have a strong hold on the subject as well. Okay, so this is something that you already know, and so that I have just written it all over. Okay, is that clear? I don't think till now everybody has an issue. Okay. Now, you know from your very childhood something called as Coulomb's law. So I'm going to spend a little bit of time on Coulomb's law also. So you know what is Coulomb's law? Everybody knows Coulomb's law. Coulomb's law gives you the force acting between the two charges. Precisely what sort of charges they are? They are static charges, and then there are point charges also. So your Coulomb's law is defined for one that is static charge, and another one is for only for point charges. So what does it say? It says that the force between the two charges is directly proportional to, you know, that Q1 Q2 upon R square, and that is equals to 1 upon 4 pi epsilon naught, and then you have this Q1 into Q2 upon R square. I don't think there's a problem till now. And if I want to write it vectorially, so for example, if this is charge Q and this is charge Q2, let's say this is charge Q1, this is, let's say, charge Q2, and let's say both are positive, then the force exerted by Q2, Q1 on Q2 would be outward, that is in r cap direction. So if I want to write this force, this vector description, it will be like 1 upon 4 pi epsilon naught, and this will be Q1, Q2 upon r cap, r square, and there will be r cap also. And instead of r cap, if I want to write r vector, then this will be 4 pi epsilon naught, and I think this is something that you know from the standard 12th classes. This will be r cube, and this will be r vector. So I don't think needs much of description. Is that clear to you? Okay. So one thing you have to keep in mind that this holds only for point charges, point and static charges, and you know that your epsilon naught is called as the permittivity. It's called as the permittivity, the free space, and that is, I think, given by some constant that is 8.854 into 10 to the power minus 12, I think, farad per meter. Okay, you just check this quantity. Okay, this is something that you already know, so I'm not going to spend much time over it. Okay, is that clear? And K, that is 1 upon 4 pi epsilon naught, comes out to be, I think, around close to 9 into 10 to the power 9, I think, Newton meter square per square. Is that clear? I think this is something that you already know. Okay.
Yes.
Okay. So you can see that this particular Coulomb's law is very important. You can see that this is the very much can say foundational sort of thing, and people think that this is just relevant to your electrostatics, but you know that when you were deriving some atomic structure thing also, then also your Coulomb's law was invoked. For example, when you know that your charge at the center is some Ze, and there is an electron revolving around it, and let's say the model of the Niels Bohr. So Niels Bohr just suggested that there are stationary orbits around which your electron revolves. So basically, what you used to do, you used to write the Coulombic potential, like potential energy, used to write by using the formula K Q1 Q2 upon R squared, right? So it not only extends to your electrostatics, rather it extends to describing a vague description of, not so, I should not say vague description, but a sort of description of, it also description of the nucleus binding the electron together. Description of electron being bound by nucleus, or probably you can say that why do your what keeps atoms and molecules together in a fluid, atoms or molecules together in fluid, and so on and so forth. Okay, so that is what I'm not much concerned in solids or probably in fluids or somewhere. Okay, so fluid by fluid I mean liquids as well as gases. Okay, and also that you know that these are the most fundamental forces of nature. Okay, so you know that there are 4 fundamental forces of nature: gravitational force, then you have this electromagnetic force, then you have this electroweak interaction, and then you have nuclear forces. So all this constitute one of the 4 fundamental forces of our nature. Okay, so overall, this suggests that that you know much about all these things. So I will go beyond, and I will just try to draw your attention to something more concrete. Okay, something more concrete. So you know that vectorially this description is given by r vector upon r cube. So whenever you have this k q1 q2 upon r square, that is sort of scalar way of writing things up. And if I'm saying that you write it vectorially, then it will be r vector upon cube. So it will be r vector upon r cube. Just give me a minute. Okay. Secondly, there is something called as principle of superposition. So principle of superposition means what? So if I have multiple charges, not a single charge, if I have multiple charges, let's say, if I have too many charges, let's say this is this. There are too many charges all around. Then all these charges are given by, let's say, Q1, Q2, Q3. Then and there are too many charges like till Qn, all of them are here. So if this is the case, then what does it say? It says that interaction of two charges, is completely unaffected by the presence of other charges. By presence of other charges. That is what freedom it gives to me. It gives to me a freedom. Let's say if I have a charge capital Q here, if I have a charge capital Q, and here you have many charges Q1, Q2, Q3, Qn line. So each of these charge will exert some force on this charge Q. So Q1 will exert some force, Q2 will exert some force, Q3 will exert some force, Qn will exert some force, and individually all these forces are unaffected by the assembly of charges in the vicinity of the charge in concern. So for example, if I have this charge Q2, whatever force it exerts on Q2 is completely unaffected by what sort of assembly it is being surrounded by. So overall, you can say that all total force will then be given by net sum of all these forces exerted. So this is what is your principle of superposition, and this is something that you know from your standard 12th classes. Okay. Okay. And understand that this particular fact is an experimental fact. This particular fact is an experimental fact. So there's no point questioning it. So overall, understand that total force is given by F1 vector plus F2 vector plus F3 vector plus Fn vector, or you can say, I think 1 upon 4 pi epsilon naught if you take outside and you take this like Q, I think you can take summation Qi, and let's say this is particular distance is given by some Ri's. For example, if I say that this is R2, this is R1, so this will be Ri square. So net force, net sum would be equals to what? K Q1 Q2 upon R square. So individually, whatever is the distance from the corresponding charge. Is that clear to you? All these things, I don't think there's an issue for now. Okay. Now, instead, I told you at the very first instance that instead, if I have this is like interaction between the charges given by the force. Okay. Now, instead, if I want to find what is the field this charge. Okay. Another thing that we know from field theory also, I'm not an expert of field theory, but what we know is, let's say if we say that both charges don't interact, what we say, we say that charges don't interact, rather their fields interact. So there is a field, and both of these charges do not interact directly, but rather their fields interact. And what is this field? So for example, if you have this charge Q, there would be certain sphere of influence that it exerts in the space. So for example, this is a charge Q. If you if you know from your childhood that if you had this kind of magnet, okay, if you had this kind of magnet with you, and you had this north pole and you had south pole, and if you brought some north pole and south pole, another magnet closer to it, and you would experience, you had this kind of an abstract experience, that is, what is that particular distance after which it starts getting repelled. So you know from your from very initial experiences of your life that, okay, there would be some distance after which you will start feeling the repulsion. Okay, so basically what is happening, there is a field that it exerts in the space and it starts getting affected by that field. So similarly, whenever you set up a charge Q anywhere in the space, there would be some sphere of influence around it, some sphere of influence around it. And obviously, this influence, sphere of influence, is a quite an abstract word to say. So what I would do, I would say how to measure it, how to measure what sort of sphere of influence this particular charge Q exerts in the space. So whatever quantity in the space, whatever thing, like whatever physical quantity in the space has some vector description as well as scalar description that are called as vector fields. Okay, so for example, this particular charge will set up a field in the space, and that electric field, how to gauge what that electric field is, what you will do, you will bring the charge very in principle small q naught. You'll bring the charge in principle small q naught. This would be your test charge, and this is what you know your as your source charge. This is what you know as your source charge. So obviously, after a while, it will start feeling some kind of attraction or some kind of repulsion. For example, this is your charge positive and this is your positive. Then in space, somewhere, this particular charge Q naught is going to feel some kind of like a repulsion. For example, if both of them are like charges, and if both of them are unlike charges, so what will happen? It will start feeling sort of attraction after a point in the space. So it implies that this particular charge has set up a field in the space, and that particular field, how to gauge that particular field, how to gauge the strength of that particular field, let us know. So what do we say? We say that what is the charge, what is the force that it exerts on this charge? What is the force that it exerts on this test charge? So what is the force that it exerts on the test charge? So force vector would be what? So force vector will be, so if this will be K Q naught upon R square. So if this charge Q exerts force on Q naught, it will be like, and let's say both of them are positive. For simplicity, if I'm taking both of them are positive, so this will be like Q naught upon R square. Is that clear to you? Now, what will be the field? So field is nothing but it is equals to force per unit charge. So what is field? So field is nothing but it is equals to force per unit charge. So what will be field? So field due to this point charge Q is given by limit Q naught tends to 0, F vector divided by Q naught vector, Q naught vector and Q naught. So this is the field. So in standard 12th also, you might have seen teachers writing this kind of definition, or instead they would be writing some different definition, and they would say that, okay, they would not say probably Q naught and Q naught tending to 0 and all those things. Instead, they would say, what is the force exerted per unit test charge? This is what they would say, per unit test charge. So what do they mean by saying per unit test charge? Because see, what I have done, I have divided by Q naught. So basically, dividing it by Q naught means what? This gets cancelled. So it implies KQ1. Instead of Q naught, you just इसको मन में बोलो 1. So force exerted per unit test charge is called as the field. So the better way of describing the same thing is that you just bring a test charge, and why this particular test charge should be 0, so that it should not much distort this particular field. Okay, so its field should be sufficiently small so that it does not quite interact and does not distort this particular field. So what we do, we bring a test charge which is sufficiently small, find the force exerted on this particular test charge, and then you just divide it. So you'll get this electric field, and this will give you the electric field strength vector, or electric strength of electric field. Is that clear to you till now? Or there is some problem with any of, or am I going too fast? I don't know. Just let me know. Am I audible? सबको समझ में आ रहा है नहीं आ रहा है?
Yes, sir.
आगे ठीक है, ठीक है, ओके. अरे एक्चुअली क्या,
सर
दिस इज क्वाइट, हाँ बोलो.
सर एक जनरल डाउट था
हाँ
कि
पूछो.
जैसे हम हम यूनिफॉर्म एज्यूम कर रहे हैं ना 1/r पे, आर स्क्वायर पे डिपेंडेंट.
हम्म
मतलब मैं बोल रहा हूँ जैसे आपने मैग्नेट का एग्जांपल दिया था ना, कुछ एक सर्टेन डिस्टेंस रहता है जहाँ पे वो एकदम से इफेक्ट
हम्म.
होता है. मतलब अ, मतलब फॉर्मूले के अकॉर्डिंग तो इन्फिनिटी पे जीरो होनी चाहिए ना फील्ड.
एक मिनट वापस में क्या बोलूं, सॉरी.
मतलब सर फॉर्मूले के अकॉर्डिंग हमारी इन्फिनिटी पे जाके फील्ड जीरो होनी चाहिए, या फिर फोर्स
हाँ हाँ, राइट राइट.
किसी भी.
हम्म
लेकिन जैसे मैग्नेट का आपने एग्जांपल दिया सर, उसमें कुछ डिस्टेंस के बाद बहुत मतलब ज्यादा फोर्स नहीं फील होती है. फिर उसको
हम्म.
अकाउंट कैसे करेंगे फॉर्मूले के अकॉर्डिंग?
उसको
मतलब
अकाउंट,
एक सर्टेन डिस्टेंस तक वो एक अलग बिहेव कर रहा है, फिर उसके बाद बिल्कुल चेंज हो रहा है सडन एकदम, मतलब एक यूनिफॉर्मली ग्रेजुअली वो चेंज नहीं हो रही फील्ड।
ओके।
तो मैं पता नहीं समझा पा रहा हूँ कि आप वो क्वेश्चन।
Um, मैं समझ रहा हूँ तुम्हारा क्वेश्चन, बट आई एम नॉट एबल टू आंसर इट राइट नाउ. व्हाट आई फील इज कि फॉर एग्जांपल, लाइक फॉर ऑल practical purposes, let's say this is my small charge q, that let's say 1 coulomb. So there would be some practical distance after which this will become exact zero. Okay, this would become exact zero. Like, mathematically it will never become zero. Mathematically it will always say no, 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 let it be r tending to infinity, and I'll not be
यस
zero anytime. So mathematically, what does it mean? It means that my force is decaying with the variation r square, 1 over r square. So obviously this will never decay in general mathematically. But for all sorts of practical purposes in physics, we know that okay, this particular charge q will start exerting some very negligibly small force. So we'll consider that force zero only. So physics and mathematics will always be at a conflict with these kind of things, because if mathematics will never say that your force would be zero anywhere in the space, but physics will certainly say that okay, what is my practical purpose. So probably for that practical purpose, that distance would do. For example, let's say for an MRI scan, you have you have a magnetic field around, like MRI machine. So probably that magnetic field would exist in feeble amount also in entire hospital itself, but they would do some sort of shielding, and that is a different stuff altogether. But anyway, there would be some practical distance after which that particular magnetic field would be, I think, zero. So I don't know what uh, I don't know, is was that the question or something else was a
हाँ,
question?
मतलब सर वो डिफाइन कैसे करेंगे हमको कितने डिस्टेंस के बाद है, क्योंकि हम तो सारे अपने प्रॉब्लम्स को इसी फॉर्मूले से सॉल्व कर रहे हैं ना, 1/r² लेके।
Right. So I would say that like for practical purposes, things would be different. Like for physical practical purposes, like for applicative side, but on mathematical end, I will write this only. मतलब मैं भी शायद नहीं समझा पा रहा हूँ, but this is what I would write.
ओके
I
सर।
do understand what you are saying, but I'm not able to explain it rightly right now. Okay. So, sure. Okay. So I'll move ahead and I'll take up your question with certain sense of
ओके सर।
understanding later on. Okay. So overall, I hope I've made you this particular picture clear. So I'm going very fast because this is all you have done in your standard 12. So I don't need to spend much time, but I wanted to spend a little bit of time so that it will not look like that I started with the problems in electrostatics and you do not have an idea about what I'm doing. So at least some idea,
यस सर।
what is field, what is potential, and what is potential energy, and what is force. So in very brief, you should understand that if you are talking about interaction between between some entities, so you would be either discussing your potential energy or you would be discussing your force. And there can be two things only. Like you can say अच्छा इस charge का इस charge के बीच में कितना potential energy, that is what is the interaction energy between the two charges or probably masses. Like here you have the entities as charges, so I'm discussing charges only. Or you can say that interaction between the two charges can be depicted by something called as force. The mechanism changes if I have to say the description of that particular force, not as interaction, but what is that effect of that particular charged entity in the space. So as a function of some xyz, there would be some quantity, and that particular quantity can either be field or it can be either be potential. We'll see how I'll be doing all these things, but in a slightly brief manner, because probably for a standard 12th class student, I would have spent probably an hour saying about all these things. But I believe that uh, you are at a better stage than those people. Okay, so I've already stated that my Coulomb's law, is only valid for my static charges. Okay, my static charges. So I am now in a fix. Let's say if I want to find the most simpler case that you start off in your standard 12th, that instead of your point charge, now I have a rod of length L. Now, if I have a thin rod of length L, so if I have a thin rod of length L, by thin I means that this radius can be taken negligibly small. So if I have a thin rod of length L, where your charge is distributed uniformly over this, the charge is distributed uniformly over this, and let's say your charge is Q. So this will be, I think, Q upon capital L. And if I want to find the force exerted by this particular rod on a point charge Q naught, which is at a distance, let's say this is your y-axis, this is your z-axis, and let's say this is your y-axis. Okay, so y, z, and then outside this would be your x-axis. So I want to find what will be the charge exerted on this point charge Q naught. Okay. And let's say this is your Z axis, this is your Y axis, and obviously this will be your X axis. This will be your X axis. Okay, so X cross Y would make Z. So every time you're in fix, you just use the right hand screw rule, and you can find that your X cross Y and this particular thing forms a right-handed coordinate system. So I don't think there is an issue till now. So what I would suggest is at least go through its electric field and potential chapter is called as that, if I correctly remember. Okay, so this is how it is. Now the point is this. Now we are in a fix. We know that okay, I have already told you that force between 2 point charges is given by Coulomb's law. But now, instead of a point charge, you have a rod of length L. Now, how would you do this particular question? Or probably how would you satisfy this particular inquiry of anyone? So what is the suggestion is, instead of going through all these things, you just take some differential small element. So I've taken a differential small element, which is dz, and this is at a distance z. Okay. Now in dz, obviously there would be some point charge only, because dz is infinitesimal small, and all these contributions from dz would eventually be integrated, and I can find the force by due to this particular rod. Okay, is that clear to you? So understand my point. Coulomb's law can only be Coulomb's law is a description given for interaction between the two charges, or force between the two charges, only if the charges are static and pointable. Like they should be point charges. So what is the way ahead? For example, if I have some continuous distributions, so if I have some continuously distributed charge, as in this particular case, so what I would do, if this continuous charge distribution is in particular uniform also, so I will define something called as lambda, which is like dq upon dl. I will define something called as sigma, which is surface charge density, like dq upon ds. This will be my thing, surface charge density. I'll write for your sake. And if I have this particular charge distributed over volume uniformly, then I would describe it as rho given by dq upon deta. Okay. And in principle, if your charge is uniformly distributed, then even if you write dq upon dl, or probably entire q upon entire l, that would be same. Because what does uniform means? It means that equal amount of charges are distributed in equal length elements. So for example, if your length element dl contains dq, then it will, whatever this particular ratio would correspond to total charge q divided by total length L. And similarly, this particular thing, net charge q divided by total area. And let's say this particular thing, net charge q divided by total volume, provided it is uniform. Provided it is uniform. Let's say if this is the case, what do I mean by uniform? Let's say if my charge density is some function of what should I say? Let's say some function of z. Now here, what does it imply? It implies that with increasing z, my charge would increase. With increasing z, my charge would increase. So certainly this is not a description of a uniform charge. Okay, so this is not certainly not a description of a uniform charge. So this is a new non-uniform charge distribution. So overall, if your charge distribution is uniform, and if it is continuously distributed, then you can define three quantities given by lambda, sigma, and rho. Lambda most appropriately is called as the linear charge density. Sigma most appropriately is called as the surface charge density. And rho is most appropriately called as a volume charge density given by the following the derivatives. I think this is quite clear to you. I don't think much explanation is needed in this account. Overall, understand that this is a vector thing. So what will happen? Another thing that you should understand, that your Coulomb's law, is a central force. Why it is a central force? It depends upon it is dependent upon the distance between the two charges. So we'll discuss these central forces in quite detail later on. But overall, this is a central force. Another prime feature. Another prime feature is this is a mutual force. Mutual force. What do I mean by mutual force? If I say this is my charge 5 and this is my charge 10 Coulomb, so it cannot be the case that 5 Coulomb would exert more force on 10 Coulomb and 10 Coulomb will exert more force on 5. No, both of them will exert equal forces. So at least for your sake, if you're teaching a standard 12th child, probably to clear their misconception, you just ask this particular question. I have asked this question to several of my standard 12 people, and several of them have given wrong answers. So anytime you ask very quickly to them without invoking a sort of rational response, because everybody is like, like everything is intuitive. Like everything is intuitive means everybody thinks by their own sort of intuition. But the subject physics itself is like it's a contradiction to your intuitions, right? So if you ask a standard 12 child very quickly, and if you say, अच्छा 5 कूलम पे कितना चार्ज लगेगा, 10 कूलम कितना लगाएगा, और 5 कूलम 10 कूलम पे कितना लगाएगा, किस पे ज्यादा फोर्स लगेगा, तो वो बच्चा पता है क्या बोलेगा? ही विल से 5 कूलम पे ज्यादा फोर्स लगेगा. And this is something that I'm telling you from my experience. This definitely is going to happen. So you will have to say to that child that, okay, so this is a mutual force. Whatever force this is exerting is equal to whatever force 5 coulomb is exerting on 10 coulomb, and 10 coulomb is exerting 5 on 5 coulomb. Both of them are exerting equal forces in magnitude in particular. Is that clear to you? So this is something that I've told you because probably you will become some teacher someday. So you'll be able to you'll be finding this particular thing that I'm telling you quite prevalent in students. Okay, so overall, understand my point that now this what is the what is the force that it exerts on this Q naught? What is the force that it exerts on Q naught? So let me write that differential element dF. So what will be the dF force? dF force would be equals to 1 upon 4 pi epsilon naught. And then let's say this particular dq dz contains charge dq. So this will be q naught dq, and divided by this is, let's say, distance y, and then it will be root over z square plus y square. So overall, this will exert a force of z square plus y square in this direction. Now, what does symmetry suggest me? Symmetry suggests me that instead, if I had not taken this charge, had I taken this charge from here, what would have happened? It would have happened that this would have exerted in this direction. So for all the elements below this rod, below this origin, the forces are in this direction. On all those elements, if I take above the origin, the forces are in this direction. So net force that would add would give me like total net forces that add are these, and these components of the forces will get cancelled. So this is something you know from standard 12th, and this would be, let's say, your theta. So overall, your net force added would be what? It will be 1 upon 4 pi epsilon. And don't do this. This is some mistake that everybody does. Everybody starts writing 2 times here. It is not 2. Like you just see from symmetry what is happening. It means that all these forces are being added. Like all these forces are being added, and they are being added on the horizontal direction. So it is just not 2. It, in fact, there are many forces. So why don't write 2? So at times, like standard 12 people, what do they do? They say that, okay, this is charge, this is charge. This is not one charge or two charge. There are infinitely many charges. So you'll have to ultimately integrate this stuff. Okay, so this is something that I'm telling you. So what would be dq? Dq would be, I think, total charge divided by total length, and there would be some dz. I think I should write dz, and then this is z square plus y square, and then what would be cos theta? Cos theta would be y divided by, I think, root over z square plus y square, if I'm not wrong. So this will be it. Is that clear to you?
Yes, sir.
So net force exerted on charge Q naught would be 1 upon 4 pi epsilon naught, and then this will be Q naught into Q into Y divided by Z square plus L Y square raised power 3 by 2, and there would be L here, and I think there would be dz here. Is that clear? I think Y would be here only. So I'll not say that Y will not be here, so Y will be here. Okay, is that clear to you? Okay. So what would be the net force? So total force would be what it would be equal to integrating this entire stuff. So F net would be integrating dF net. And from your standard 12th, you know already that this will be 1 upon 4 pi epsilon naught. This will be L will come out, Q naught will come out, Q will also come out. And then you have this Y will also come out. Okay. And then you have this Y will remain, no? Y would anyway remain. Okay. So, and this will be dz upon z square plus y square raised to power 3 by 2. And this is, if this particular rod is it is of length L, then from where to where I'm integrating? I'm integrating from below to above. So if this is my origin, then this will be minus L by 2 and this will be plus L by 2. Is that clear? Because I have kept my origin here. So this will be minus L by 2 and this will be plus L by 2. So, okay. So I integrate from minus L by 2 to plus L by 2. Is that clear? I don't think there is a mistake. And if you want to integrate this stuff, just write z is equal to y tan theta, and I think things will be done. So this will be like y is a constant, secant square theta, d theta. So if I write y secant square theta d theta, and if I just write here, it will be, I think, y cube, and then I think it will be secant cube theta. Like, is that clear? And I'll put all these things later on, but overall understand my point. And then this particular thing would be equals to what? So this is y, this will be y square, and again a y is here. So overall this will be q naught q divided by 4 pi epsilon naught y, and then there will be L. And this particular integral is 1 upon cos sec theta. This will be cos theta. Cos theta integration is sine theta. And what would be sine theta? You just find what would be sine theta. Sine theta would be z upon root over. So sine theta would be z upon root over z square plus y square. From where to where? From minus L by 2 to plus L by 2. So if at all, I want to write this finally, and I can also write my q by L as some lambda also, if I want to write it. So if I don't want to write it, I'll keep this all going. L, this will be L by 2 upon root over z square plus L square by 4, and then again minus this will be plus, so this will be 2. So overall, you understand that your total force is given by K Q naught Q upon Y into L into root over Z square plus L square by 4. So overall, this gets cancelled, and this will be your answer. I think total answer would be, I have written L square by 4, yeah, Y square 1. अपन Z की जगह replace करें, so Y square plus L square. Is that clear to you? I don't think there is an issue till now. Now, if your y is 2 greater than L, so if your y is 2 greater than L, matlab, if your charge Q is placed very, very greater than L, then your force net will be equals to KQQ naught upon simply y square. So it would be like a point charge Q placed instead of this rod like that. Is that clear to you?
Okay,
this is something that you know. Okay. So I'll take another lecture on this particular thing. Just give me a minute.